Welcome back. Now we're going to have a deeper look into the observation space and how we can modify it in order for our model to learn faster and perform better. The observation space is the picture that is fed into the model itself, and the model comes up with a prediction for the next best action, and then this action is fed again into the environment, which takes its next step and provides the next observation. Now this observation space can be changed using wrappers on the environment. When we created the environment, we first have an Atari environment, which has something like 210 rows, 160 columns, and 3 different colors. We have then put this into the Atari wrapper, which besides some other things scales down the observation space to a square of 84 times 84 and only one dimension because it's only grayscale. And after that we have the frame stack wrapper, which saves the last 4 time steps, so the time between tn and tn minus 3. And last we're going to vectorize this thing with the number of environments. Now we're going to look into the code, and the first code base, the 3.1, will only focus on the first 2 elements here, the original observation space as well as the Atari wrapper. In the 3.1 observation space script, you will find that the beginning is very similar to what we had before, the same hyperparameters. We are using almost the same wrappers. In here we're using the full Atari wrapper, so the one that includes the scaling to the 84 times 84 grayscale image. Then instead of training a model, we're loading the model that we had already trained from the baseline. And then we're going to see how it plays. We're going to take the observation space, which we get when resetting the environment, as well as when we take a step. And we take the image, which is taken from the render function. And the difference is the observation space is what is available to the machine, to the model when we train, whereas the image is an image intended for a human being. So it's usually the image of the original environment. We're going to go to step 23. That's more or less an arbitrary choice. I've chosen it such that the ball is still in the game. And I'm going to export the images as JPEGs, and I'm going to export the arrays as CSVs. For the arrays, the important piece is that we choose the correct dimensions to take. When we look at the observation, the shape, we see it's an 84 times 84 and has a stack of 4, which is because of the frame stack, which is only applied to the observation space but not to the rendered image. And on the rendered image, we're just going to take the first color channel. Doesn't really matter that much. The values will be slightly different, but the patterns will still be the same. Now on the left, you see the observation space as the model sees it in grayscale, and on the right you see it as it is rendered to a human or as it is rendered without any wrappers. And what you immediately notice is, well, it's smaller, it's grayscale, and it's kind of blurry. This being blurry is even more evident when we look at the CSV files. On the left side you see the observation space, on the right side you see the original image. And what you notice immediately, here it's always 142 and a hard green against a solid red, whereas here it's a bit smoothed out. And I assume it's because of the downscaling that for a pixel, it takes something like the average value of the pixels around it. And it becomes even more pronounced when we look for the ball and the pad. On the right side, on the original image, you see the ball really has a hard 200 all the time with only zeros around it, whereas on the observation space it gets a bit more blurry. And we can also assume that when it travels through the screen that these values might change. So recognizing the ball, I would say it's much harder on the observation space after the warping of the image compared to before. And that's also the reason why when we set up our observation space, we will not use this warp wrapper. Instead, we're going to implement our own wrapper. On the left side, you see the original observation space, the image provided by the Atari game environment, and on the right side, you see what we intend to feed into our model. The three noteworthy differences are the monoscale, so take out all the color and just let the color be either white or black. The second piece is we trim the borders because there is no relevant information in those borders. Yes, you have the score and the number of lives, but this should not affect in any way the decision made in which direction to move the pedal. So it should not affect the inner workings of our model at all. Lastly, we have an aimbot. What happens is we're looking at the position of the ball. We're also saving the last position of the ball, and we're extrapolating where it will hit the pane of the pedal. And at this point, we're adding another small piece here on the right side, telling our model this is where the ball will hit. Now just imagine playing this Breakout game and already having a heads-up display that tells you this is where the ball will be. This should really give our model a leg up. We have three flags in here. The first flag is about the color, whether we want to keep all three colors. We want to grayscale it, but keep the number of 3 color dimensions. We want to grayscale it and only have 1 color dimension, or we want to only have black and white. The reason why I implemented both 3 and 1 dimension for the grayscale and the mono was that I had some issues with reducing the dimensions of the observation space and not getting consistent results. And I wanted to understand whether that's because of the grayscaling or because of the change of dimensions. It turned out to be a bug. In the end, the 1-dimension grayscale performs just as well as the 3-dimension grayscale. The next flag is about the dimensions of the picture, whether we want to keep the size of the picture, whether we want to trim away the sides of the picture, or we just want to override the sides of the picture with blacks or whites. And the last flag tells us whether we want the aimbot turned on or off. Now in the init you will find a lot of different hard-coded variables. We're not going to go into depth with them right now, but later in the code when they are used. We need to define the observation space because it might have changed. When we were using trimming or we changed the number of colors, we need to redefine the observation space so the model knows kind of what values to expect. I had a bug in the beginning where I used monoscale and set it only to 0 or 1, but still left the observation space going between 0 and 255. So the whole normalization was messed up. Now let's look at the observation function. This is what is called each time a step in the environment is taken, and the first thing it checks whether it needs an aimbot or not. So let's skip that for the time being and first look at the trimming and the color space. Here, if we have a trim, then what it does, it just takes the hard-coded thresholds for where the screen ends and begins, where the left and right boundaries are, and crops the array. If the dim is set to black nor white, then it will just override the color in those spaces, either with zeros or with 255s. Lastly, for the coloring, either it's 3 color, then nothing happens, or if we set it to grayscale, it will just take the max of the 3 color channels and write the max into the 1 remaining channel. And for the mono, it will just take the max and compare it to the threshold and then multiply it by 255. So the only values it can take is either 0 or 255. Now let's look at the aimbot. The aimbot will only look for the ball in the space between the pad and the bricks. So only in the area between here and here, because only here the ball is the only thing. So what we need to do is we need to check each of the pixels in between and see whether they're above a certain threshold. And if yes, we know the indices where the ball is. If it finds the ball, it just saves the ball's row and column, so the x and y axis, and maybe it doesn't find the ball because it's somewhere up with the bricks. Now it checks whether it has found the ball and whether it has found the ball last time. So you see the self.ball last column. It basically is just the ball's last location. We need both of them to calculate the velocity in x and y axis. And then only if the ball flies downward, so only if ball velocity is bigger than 0, we're going to make a prediction. If the ball flies upward, the calculation would just tell it where the ball came from. So we're calculating the time to impact and then the predicted impact column. And since the ball might be bounced off one of the walls, in order to model the bouncing, imagine the play space to go from 0 to 1. The ball is somewhere in between. It has a velocity. It will go that way. And it might go to something like 1.4. So this is the unbounced x, and we want to calculate now the bounced x, so where it goes instead, and that's our y. Now plotting x against y. Y by definition goes from 0 to 1, and if we don't bounce at all, it just is the same, is identical. If it bounces once, it goes the other direction until it reaches 2, then it goes up again until 3, and down again, and so on. So you have x here, you have y here. And now let's count the number of bounces. We have 0 bounces before the 1, then we have 1 bounce, 2 bounce, 3 bounce. Now it's important to see whether the bounce is an even number or an uneven number. As long as we are in the even numbers, then the only thing we need to do to get from the identical transformation down to what we want is subtract the number of bounces. So if b is even, then y is something like x minus bounces. And if b is odd, then we're taking y to be 1 minus x minus b. So the x minus b tells us how far did it travel downwards, and the 1 minus as well travels downwards from 1. So it's 1 plus number of bounces minus x. Now back in the code, you have all of these calculations in here. You calculate the number of bounces, you look whether it's an even or odd number of bounces, and as I explained, you then calculate the predicted impact. And last, we add the predicted impact to the image that we then write into the observation space. And finally, running this code gives us the 2 images you've already seen on the whiteboard. Now let's go to the code 3.3 aimbot training, where we're taking this observation wrapper that we just created and put it into a proper training and see how well it performs against our baseline model. Here on the tensor board you see how the baseline, the blue one, performs against our model now based on this new wrapper. And I've run a lot of different variations of the new wrapper, and this is one of the best performing ones. Now, since I've trained a lot of different variations of the model with this observation wrapper, with trimming turned on and off, with color space turned on and off, and with prediction turned on or off, and with different hyperparameters, I think it makes sense to first take a step back, take the exact same model and just train it a bunch of times with different seeds. And what you see here is that even though everything is exactly the same, with different seeds we get something like plus minus 10. You see the average reward here at the end is has a spread of 20. And I assume if we run more of these, more different seeds, it will spread out even further. So my gut feeling is anything that is something like plus minus 15 is not really significant, and you can't make a statement whether it performs better or worse. Now let's look at the impact of the frame stack. The wrapper that takes past frames and appends them to allow the model to kind of remember what happened before. So this is the curve with a frame stack of 2. We end up at something like 48. If we increase the frame stack to 3, we get a vastly better result with 68. With 4, it again drops to the same number as 2. And with 5, again, it's as good as 3. So there might be speculation, it depends on being odd or even. So I trained a bunch of other models to see whether that holds up. With 6, again, we see it in the same realm as 2 and 4. 7, again, is better. But here it seems to break down. 7 and 8 are almost the same, and 9 as well. So it doesn't seem to matter for 7, 8, 9 that much, they're in the middle, but the exact number of frame stacks seems to matter for the lower numbers. So either we will go with 3 or 5. The other piece that is relevant obviously is how long it takes to train them. But since I'm training several models at the same time, usually these numbers are a bit distorted. So you can look at the relative time and you see how long it took to train them. You see the red one with a frame stack of only 2 only took me 0.7 of an hour, whereas the one with 9 took double the time. So in general it makes sense, the more frames you stack, the longer the training time will be. It doesn't hold up 100%, as I said, because I tend to train several models simultaneously, and that kind of artificially slows down a model. Still, what we see here is that a frame stack of 3 and 5, and here also the 2, have the best return on training time. Now let's look at the effect of the trimming of the boundaries, the non-game area. And what we see is if we keep the boundaries, we have the red line, and it outperforms the case where we just whiten the boundaries, the blue one, or even more outperforms the case where we trim it. Now this is a bit of an unexpected result, because our hypothesis was that the boundaries should not matter. They don't really serve a purpose in making a decision where we want to go with the action, but yeah, it seems to matter. So I reran the whole thing with slightly different parameters, in this case with a frame stack of 3. And what you see here is the red one now is the trimmed version, the green one is the version where we keep it, and the blue one is the version where we whiten the boundaries. And the picture basically reverses. So the one thing I would take out of it is it doesn't really affect the performance of the model, at least not sufficiently to make a clear statement. The variance in our observations was just playing a bit with other parameters outweighs the choice of whether we want to trim, widen or keep the boundaries. Now we're looking at the impact of our aimbot. How much does it make life easier for the model? You see the blue line is if we turn off the aimbot, and the orange line is if we activate it. And you see the aimbot clearly outperforms the non-aimbot version of the wrapper. And now let's do the same thing again, this time without a trim, but instead a widened boundary, just to see whether the results are consistent. And you see the same here. The pink line is the where we don't turn on the aimbot, and the orange brownish line is when we turn it on. And I wanted to play around and add one more piece of code where we write down the main variables and code them as pixels. I called that predict counters. So when we look at the overall observation space here. We have somewhere the pad, we somewhere have the aimbot, we have the ball, and we have all of the bricks. What I did is I encoded the time to impact as the first pixel. I encoded the relative position of the aimbot, from 0 to 1 as the second pixel. And the third and the fourth pixel would be the ball's location, so the column and the row. And the last pixel would encode the position of the paddle. Now you will find the corresponding code inside the observation wrapper's observation function. There is a check whether we want to predict counters. First we override all of the 5 pixels with a black value. And then I write the time to impact, the prediction, the coordinate of the column, the ball's column and the ball's row. All of them were normalized, and then I write down the position of the pad. So with these 5 pixels, I believe it should be able to play the game without seeing anything else, because it knows where the pad is, it knows where the ball is, it knows when and where the ball will impact. Now when we look at how this model performed, first keep in mind that the pink line is without any aimbot, the orange line is with the aimbot turned on, but without these 5 special pixels. And with these 5 special pixels, well, it's not clearly worse, but it's also not clearly outperforming the aimbot. I assume it's because of the way the PPO model has its layers set by default. In my understanding, they're using convolutional layers, meaning you have a kernel going over that picture, so it's not really intended to deal with pixels that encode individual pieces of information by themselves, but more with the shapes within the image. It might be worthwhile following up on this idea by redefining the observation space, having one observation space being the picture and another observation dimension basically with these values. Now we have played around with the different hyperparameters as well as the different options that we had implemented in the observation wrapper, and I would say this is our best model so far, partially because it was clear that it outperforms, especially on the aimbot. Other pieces are more like gut choices, something like trimming or reducing the color space. Didn't really show a significant improvement, but I just personally feel better with it, and there was no strong red flag against it. Now we see here the 3 lines from the 3 different seeds, so the truth will be somewhere in the middle. We have a feeling for the variance of it. And now if we compare it to our original baseline, I would say we have done significantly better. Instead of a score of something like 13, we now get scores between 60 and 80. And the other good thing is it still has a relatively linear slope, meaning if we would just run the training process, 10 million steps of 1 million, we can expect significantly better results. So now we have taken some time exploring the observation space and how we can modify it to make our model learn faster and be more efficient. In the next chapter, we are going to look into model selection as well as hyperparameter tuning. Thank you, and have a nice day.